Well, hello, ladies and gentlemen. Let's move on. We derived last time the saturation dome by heating water isobarically. We started off with a liquid H2O. We heated it through into a saturated mixture, and then up to a superheated vapor, and we developed the saturation curve and the saturation dome, if you like. So we're going to do an example today. Couple examples involving using the saturation dome to figure out the state of a particular substance. And then after we do a couple examples involving the saturation dome using the TD and the PV plot, we're going to move on to properties inside the dome. So when we have a saturated mixture, when we're inside the dome, it's a mixture of saturated liquid and vapor, how do we characterize the mixture? Well, we're going to introduce the quantity called quality. A quality of the mixture. We'll define that and derive an equation for it in due course. And then we'll do an example involving quality. So we're going to spend today on the saturation dome, and then we're going to look at calculating properties within the dome using quality. Okay? Okay, so we're going to start off with an example here. We're going to have H2O at pressure of 5 bar and a temperature of 151.9 degrees C. Very precise temperature. And we want to find the state or the phase. What is the possible state or phase of this H2O? Okay? All right, so let's get started with that. So we have a pressure 5 bar. We have a temperature of 151.9 degrees C. Okay? So I'm going to first try to find out what the state is using the TV diagram. And then we'll do the PV diagram afterwards. So here's TV. T is going to be in degrees centigrade. And specific volume will be in cubic meters per kilogram, okay? Now let me put up the saturation dome. Okay, and I'm going to put in an isobar, my 5 bar isobar. Pressure equals 5 bar. Presumably my material, my H2O, is somewhere on that isobar, a 5 bar isobar. Now to figure out where we are, I need temperature, or I need a specific volume. I need something to lock up the horizontal or the vertical position. I know I'm on the isobar, so if I know a specific volume or I know a temperature, in theory, I can get the state or the phase, all right? So the first thing I'm going to do is I'm going to look up the saturation temperature. I got a temperature, it's 151.9 degrees. I'm going to look up the saturation temperature of my H2O at 5 bar. So I'm going to look up T-sat at 5 bar. That's the first thing I'm going to look at, okay? So T-sat at 5 bar. Well, so if you go to your textbook here or to the notes, let me show you what we got here. So here's the PDF of your notes. So I encourage you to either get the textbook or to get the notes. And if you go to the very end of the notes, you see a bunch of tables. So index, appendix B, property tables. Don't worry about table B1 yet. It basically gives chemical formulas, molecular weights, critical temperatures and pressures for various substances. Don't worry about that. What we are interested in are these saturation tables. Saturation tables. As a function of temperature, we get boiling pressure, we get specific volume for the saturated liquid, and specific volume for the saturated vapor, and some other stuff. So these are saturation tables. Let's look at this saturation pressure table. So instead of having temperature in the first column, we got pressure in the first column. Pressures in bar. Let's see here. We are at a pressure of 5 bar. Here's 5 bar right here. The boiling temperature or saturation temperature at 5 bar is 151.9 degrees C. So Tsat at 5 bar is 151.9 degrees C. And by the way, that's also equal to our temperature. Equals T. So we're at the boiling temperature, precisely. So Tsat of 151.9 degrees C. That's also equal to T. Okay? That means we're somewhere here along the isobar. We are a saturated mixture of some kind. We could be a saturated liquid, or we could be a saturated vapor, or somewhere in between. The point is, we are some kind of saturated mixture. Saturated mixture, okay? If I was below 151, I'd be a supercooled liquid. If I was above 151.9, I'd be a superheated vapor, okay? So we are at Tsat. That means we are a saturated mixture. Let's do the same thing with the PV plot. Pressure, specific volume. Here's our dome. Here's my isotherm. Okay. Now I'm at 151.9 degrees C. I guess this pressure is in bar. Okay. So I'm somewhere on this isotherm. Somewhere on the isotherm. Now, what is the boiling pressure at 151.9 degrees C? The answer is 5 bar. Tsat at 5 bar is 151.9 degrees C, but that also means that Psat at 151.9 degrees C is 5 bar. Okay, you see that? 151.9 degrees C is the boiling temperature at 5 bar. So the boiling pressure at 151.9 degrees C is 5 bar. Another way of saying the same thing. So this is 5 bar. Psat at 151.9 is 5 bar. Okay? And that also is equal to our pressure. So Psat is also equal to P. Saturated mix. We are somewhere along this isotherm within the dome. Okay? Saturated mix. Saturated mix. Saturated mix. Okay? That's the first example, saturated mixture. Let's do the second example. Oh, shoot. Damn. Okay, again, boiling temperature at 5 bar is 151.9 degrees C. That means we are along the isobar somewhere in the dome. This is our temperature, and it intersects with our isobar inside the dome. Therefore, we are a saturated mix. For the PD plot, pressure, specific volume, we are at 151 degrees C, and our boiling pressure at 151 is 5 bar, which is also our pressure, 5 bar. So that means we're somewhere along the isotherm within the dome, okay? Could be a saturated vapor, could be a saturated liquid, could be a mixture, okay? Some kind of mixture. Sorry about that. I always forget to turn these things back. Okay, let's do another problem. Let's do another problem. H2O. And instead of 5, tell you what, we're going to leave it at 5 bar, but we're going to crank up the temperature. 200 degrees C. Let's find the state. Here's our TV. And here is our PV plot. It's our dome. There's our dome. There we go. So we are on 5. So let me put in the isobar. So here is our isobar. 5 bar. Isobar. And again, the boiling temperature, Tsat at 5 bar is 151.9 degrees C. We got that from the previous problem. That's our boiling temperature, okay? Now we are above that. We're at T equals 200 degrees C. The intersection of my 200 degrees C isotherm and my 5 bar isobar is right there. That is the state. That is the superheated vapor region. Superheated vapor region out here to the right of the dome. So temperature, which is 200 degrees C, is greater than Tsat at 5 bar, which is 151.9 degrees C. That implies superheated vapor. We are hotter than the boiling temperature, so we are superheated vapor. We're at a higher temperature than the boiling temperature, superheated vapor. Okay? Put a little box around this superheated vapor. Okay, what about the PV plot? Let me put in an isotherm. So here's my 200 degrees C isotherm. 200 degrees C isotherm. I guess I'm going to need this space. So I'm going to look up the boiling pressure at 200 degrees C. Tsat at 200 degrees C. I'm going to look that up. Let's go to our saturation tables. Okay, I want temperature here, table B2, saturation temperature table for H2O. 200 degrees C, the boiling pressure is 15.54 bar. 15.54 bar. This is in bar. Okay. Now we are at 5 bar. Intersection of the isotherm and the isobar. Isobar is horizontal, the isotherm you can see here. 200 degrees C isotherm puts me in the superheated vapor region. Superheated vapor. Mathematically, Psat, which is 15.54 bar, is greater than the pressure, which is 5 bar. Our actual pressure is below the boiling pressure, so we're in a superheated vapor. Superheated vapor. Superheated vapor. Okay? Our pressure is below the boiling pressure, superheated vapor. Our temperature is above the boiling temperature, superheated vapor. Okay? Let's do a last problem here. Let's do, PSAT, 200 degrees C, 15.54 bar. 15.54 bar. We're at 5 bar. Intersection of my 5 bar isobar and my 200 degree isotherm gives me the state, superheated vapor region. Another way of saying that is our pressure, which is 5 bar, is below the boiling pressure at 200 degrees, superheated vapor. Let's do another problem. Let's crank up the pressure to 2.5 megapascals. 2.5 megapascals. Let's crank up the pressure. So now we have pressure and temperature, and a much higher pressure this time. Let's crank up the pressure. Crank up the pressure. Let's see here. Pressure 2.5 megapascals. And what's our temperature? Our temperature is going to be 200 degrees C again. Temperature 200 degrees C. Let's find the state. TV and PV. Pressure is going to be in bar, and temperature is going to be in degrees C. Okay. Okay, so let me put in a saturation dome. Here's my isobar. This is pressure equals 2.5 megapascals. By the way, 2.5 megapascals, let's see here, let's convert that into bar. Pressure 2.5 megapascal. Let's see, a megapascal is what? 10 to the 6 pascals. Oops. So 1 megapascal is equal to 10 to the 6 pascals. Okay? And 1 bar is equal to 10 to the 5 pascals. Okay? 1 bar is 10 to the 5 pascals. Notice the pascals cancel and the megapascals cancel. And I get 25 bar. Okay, so 2.5 megapascals is 25 bar. Let's look up the boiling temperature, or TSAT. TSAT at 25 bar. Let's look at TSAT at 25 bar. I hope I have it. We will see. Let's see here. Oops. Try to switch it off this time. Okay, saturation temperature tables, saturation pressure tables. 25 bar. I actually don't have it. I have 20 and 30. So I am simply going to take the average of these two. Let's do the simplest interpolation we can do. We're right smack in the middle of the two. So let's see here. I have 233.9 plus 212.4, and I'm going to divide that by 2, and I get 223.15 degrees C. 223.15 degrees C. Okay? That's from just doing a simple interpolation. We're right smack dab in the middle between two data points. So I have 223.1 degrees C. I'm going to put an approximately equal here. Okay? So this guy is approximately 223 degrees C. Okay? 223 degrees C. Now we're below that. We are at 200 degrees C. That's our temperature. Intersection between the isobar and our isotherm puts us in the supercooled liquid region. This temperature is greater than 200 degrees C, which is our temperature. Tsat at 25 bar is greater than 200 degrees C, which is our temperature. So we are cooler than boiling. Cooler than boiling, super cooled SCl, super cooled liquid. Super cooled liquid, SCl. Super cooled liquid. Okay. Let's do the same thing on the PV plot. Here's our isotherm. So this is 200 degrees C. Let's find our boiling pressure at 200 degrees C. Let's find our boiling pressure, or Psat, at 200 degrees C. This one we might be able to find this one. Let's have a look. Pressure table, saturation temperature table. 200 degrees C, 200 degrees C, 15.54 bar. Psat at 200 degrees C, 15.54 bar. 15.54 bar. 15.54 bar. So that means Psat at 200 degrees C, 15.54 bar. Okay? Now we are at 25 bar. We're actually at 25 bar, so this is 25 bar. That's my pressure. Intersection between our isotherm and our isobar puts us in the supercooled liquid region, SCl. Psat at 200 degrees C is less than P. Our boiling pressure is less than 25 bar, so we're super compressing it. So we got a super cooled or compressed, super cooled liquid. Okay? Okay, that's how these phase diagrams, saturation dome problems work. Okay? Put in an isotherm, you put in the saturation dome, you put in some isobars and isotherms, or isocores. You got volume here, specific volume. And you see where the intersections are, and that's where you know the state is. Okay. Okay, so we've talked about using the saturation dome to determine the phase. In other words, the state. So remember here, just go over this one more time. TV, isobar. So we got supercooled liquid here, superheated vapor, SHV, And then inside we have a saturated mix. And over here, here's the critical point. Critical temperature and pressure. And over here, we got saturated liquid. And here we have saturated vapor. Vapor over there on that edge of the dome. Okay. Now it turns out, knowing temperature and pressure, we can do, if we're in the superheated vapor, supercooled liquid region, that's enough to define the state. Over here in the superheated vapor region, if we have temperature and pressure, that's enough to define the state. But if we're inside of the dome or on the surface of the dome, having temperature and pressure is not enough to describe the state. For example, what if you are on this part of the isobar? You need to have a way of describing whether you're a saturated liquid, a saturated vapor, or somewhere in between. So if you're in here, we need something besides temperature and pressure to define the state. And that something is called the quality. Quality, symbolized by X. X is defined to be equal to the mass of the saturated vapor divided by the mass of the saturated mix. It basically tells us the mass fraction. It's the mass fraction of the vapor component in our mixture. So let's say we got a mixture here. Here's saturated liquid, and here's saturated vapor. I need to know either a temperature or pressure and a quality to define the state. Okay? Now I want to show you some limiting cases for quality. When quality equals 0, quality equals 0, that means the mass of the saturated vapor component is 0. There's no saturated vapor in the mixture. That means we are all saturated liquid. So right here on this side of the dome, quality equals 0, okay? Saturated liquid. If X equals 1, that means the mass of the saturated liquid is equal to the mass of the mixture. So it is all saturated vapor. So out here, quality is equal to 1 at that point, okay? 0 saturated liquid, 1 saturated vapor. That's how quality tells us the state. And of course, in between 0 and 1, we can be anywhere along this isobar, okay? Now, let's try to get an expression for calculating quality. Let's calculate quality. Let's get an expression for calculating quality. Okay, how do we get quality? Well, let's put up our container here. So this is our mixture. This is our mixture, and our mixture has a certain mass. Okay, our mixture has a certain mass, and a certain volume, V mix and M mix. The vapor component has a certain mass, so M sat vapor, and it also has a certain volume, V sat vapor, okay? And so does a liquid. M sat liquid, V of the sat liquid. Now, these liquids and vapors, these saturated liquid and vapor, also has a specific volume. So we also have V, lowercase v, for the saturated vapor, and specific volume for the saturated liquid, okay? And the mixture itself has a specific volume. V sat mix. That would be the total mixture volume divided by the total mixture mass. All right? Okay, let's try to develop a way to relate the specific volume for the mixture to the specific volume to the vapor and the specific volume of the liquid component. Let's figure out a way to relate all these specific volumes. So let me write down two equations here. First equation is M of the mixture mass. The whole mixture is equal to two masses added together. The mass of the saturated vapor. I'm not going to write sat anymore. I'm just going to write vape. Mass of the vapor plus mass of the liquid. Okay, so that's a mass balance applied to the mixture. The mixture mass is equal to the vapor mass plus the liquid mass, saturated liquid and vapor, okay? Also, the mixture volume is equal to the the volume of the saturated vapor plus the volume of the saturated liquid, okay? And that's again by applying a volume balance to my mixture, okay? All right, let me rewrite this equation in terms of masses and specific volumes. Specific volume of my saturated mixture. Volume of my saturated mixture is equal to the mass of the mixture times the specific volume of the saturated mixture, okay? Specific volume times mass gives you volume. The volume of the vapor component is equal to the mass of the vapor component times the specific volume of the vapor component. And the volume of the liquid component is equal to the mass of the saturated liquid times the specific volume of the saturated liquid. Okay, so I've rewritten the equation in terms of masses and specific volumes. Okay, let me divide this equation by M mix. The mass of the saturated mixture. Okay? Well, these cancel out. Okay? Mass vapor over mass mix. That mass vapor over mass mix. That is my quality. Mass of the saturated vapor over mass of the saturated mixture. That is my quality. So I'm going to replace that with an X. Quality. All right. Now this term here, we're going to have to massage this a little bit more. I'd like to get a quality out of that term. I'm going to notice from my mass balance But mass of the liquid is equal to mass of the vapor minus, mass of the mixture minus mass of the vapor. So this mass liquid is equal to mass of the mix minus mass of the vapor. And then I've got M mix in the denominator. Okay, and that's for my mass balance. I'm simply solving for mass of the liquid. Mass mix minus mass vapor. Well, this is equal to mass mix over mass mix is 1, minus mass vapor over mass mix gives me quality. So that fraction is equal to 1 minus the quality. Let's collect terms and see what we get. Specific volume for the saturated mixture is equal to the quality times the specific volume of the saturated vapor plus 1 minus the quality times the specific volume of the saturated liquid. Okay, so let's massage this a little bit more. I'm going to group together all the terms involving quality in this equation. This term and this term. I'm just going to group it together. And I get specific volume of the saturated liquid plus quality times the difference in specific volume of the saturated vapor and the specific volume of the saturated liquid. So let's write down what I got. Specific volume of the mixture is equal to the specific volume of the saturated liquid plus the quality times the difference between the specific volume of the saturated vapor minus the specific volume of the saturated liquid. Okay? Put a box around this equation. This equation allows us to calculate the specific volume for the mixture if I know the quality. You give me the quality, and presumably I know temperatures or pressures, so I can look up the specific volumes for the saturated liquid and vapor. Presumably, where would I look those up? Where would I look up specific volumes for the saturated liquid or vapor? Well, I could do it here. We'll do an example here soon. Temperature table, specific volume of the saturated liquid and vapor, right here, okay? Right here. You give me a temperature or a pressure so I can get specific volumes for the saturated liquid and vapor. You give me a quality, I can give you the specific volume for the mixture, okay? Of course, I can solve for quality. I can also say quality is equal to the specific volume of the saturated mixture minus specific volume of the saturated liquid divided by the difference between the specific volume of the saturated vapor and saturated liquid. So this is another version of the same equation, okay? You give me specific volume for the mixture, and I can give you quality. All right? Now, one little thing I want to point out before we move on and we do an example is this whole derivation could have been done with internal energy. I have a U of the mix. I have a specific internal energy of the mix. I have a U for the saturated vapor. I have an internal energy, specific internal energy for the saturated vapor. Same thing for the liquid. I could have done this in terms of internal energy instead of volume. And I end up with a similar equation. U of the mixture minus U of the saturated liquid divided by U of the vapor, U of the saturated liquid. I could have done this as well. Okay, I could have done this. I'm not going to do the derivation. I think volumes is more easy to understand. But that equation, this equation here works for specific internal energy as well as volume. So does this one. I could put U's in there instead of B's. Okay? Okay. Let us do an example. Let's do an example. Let's say we have H2O. And this H2O is in some kind of container. Some kind of container. So given H2O, we got how much H2O do we have? 0.01 kilograms. So schematic. We have some kind of a container here of H2O. And the mass is 0.01 kilograms. Okay. Now I am also at a pressure equal 100 kPa, 100 kPa or 1 bar, 100 kPa. Okay, pressure is at 100 kPa. And the volume is 0.015 cubic meters. So volume 0.015 cubic meters and pressure is 100 kPa. All right. Okay, let's, what are we supposed to find? Find the state. Find the state. If the state is a saturated mixture, let's find the quality. And let's find the internal energy, U of the system. Okay? All right. Analysis. Analysis. All right, let's put up a TV plot. I could do this using a PV plot, but I think I'm going to stick with a TV plot today. So we have a pressure of 100 kPa. By the way, let's convert that into bar. So a bar is a 10 to the 5th pascals, and a kPa is a 10 to the 3. So 1 bar is 10 to the 5th pascals, and there are 10 to the 3 pascals per kPa. kPa's cancel out, pascals cancel out, and I get 1 bar. Okay, so I'm at 1 bar. Isobar. 1 bar. There's my isobar. I'm somewhere along that. Okay, well, let's count. So I need another property. I know I'm on this isobar somewhere, but I either need a temperature or I need a specific volume to locate where I am on this isobar. Why don't I look up the specific volume of the saturated liquid and vapor at 1 bar, and then calculate the specific volume for the mixture and see where I am. Okay, let me calculate some specific volumes here. So let's look up the specific volume of, let's look up the specific volume for the saturated liquid and vapor at 1 bar. Let's do that. Specific volume of the saturated vapor at 1 bar. Specific volume of the saturated vapor at 1 bar. Let's look that up. And let's also look up specific volume. Let's do it this way. Specific volume of the saturated liquid at 1 bar. Let's look those both up. So let's go to our saturation tables out of the book or notes. 1 bar, let's go, this is a temperature table. We got temperatures and then pressures. Maybe we can go to a pressure table. Bar temperature, specific volumes for the liquid and vapor. Here's 1 bar right here. That's just a little bit below an atmosphere, so 99.63 degrees is the boiling temperature at just below 1 atmosphere. An atmosphere is 1.01 bar. Specific volume for the saturated liquid, 1.0432 times 10 to the minus 3. See, V sat liquid is equal to this. So V sat liquid times 10 to the 3 is equal to this number. So specific volume is 1.04 times 10 to the minus 3. I'm going to write that down over here. 1.04 10 to the minus 3, and that's cubic meters per kilogram. Let's look at V stat vapor. 1.694. 1.694. 1.694. Okay, let me switch the camera back again here. 1.694 for the saturated vapor. Okay. All right, now let's calculate the specific volume for the mixture, for the H2O. Specific volume for the H2O. I don't know what it is right now. For the mixture. Well, that's going to be the volume of the H2O. I guess I'll call it H2O. Let's calculate the specific volume for the H2O. The volume divided by the mass. Let's see here. We had 0.015 cubic meters, and I've got 0.01 kilogram of the stuff. Units are cubic meters per kilogram. That looks pretty good. That looks pretty good. So let me crank this out. Let's see here. Well, I guess I just moved the decimal place over twice. 1, 2. 1.5 cubic meters per kilogram. Okay? 1.5 cubic meters per kilogram. All right, let's take what we know and put it in our TB diagram. I know V stat liquid is equal to 1.04 10 to the minus 3, and this has units of cubic meters per kilogram. Okay, and I know V stat vapor 1.694. Those are all from saturation tables, okay, 1.694. However, my specific volume for the H2O is between the two. It's 1.5. So I'm actually along this isochord. 1.5 cubic meters per kilogram. The intersection of my isophore and my isobar, that is my state. Saturated mixture. Saturated mixture. Okay. So V sat liquid is less than V for my H2O, which is less than V sat vapor. My specific volume is in between V sat vapor and V liquid. Therefore, I am a saturated mix. Saturated mixture. Okay? You can see that on the plot. You can see that on the plot. Let's calculate the quality. X. Well, that's going to be equal to V of the mixture minus the specific volume of the saturated liquid divided by the specific volume of the saturated vapor minus the specific volume of the saturated liquid. Okay, this is from our previous derivation. All I got to do is plug in numbers. Let's see here. 1.5 minus 1.04, 10 to the minus 3. And all that will have units of cubic meters per kilogram. And then I have 1.64 minus 1.04, 10 to the minus 3. And that all has units of cubic meters per kilogram. The units cancel out. Dimensionless, dimensionless. X is dimensionless. Quality is dimensionless. And I get a quality. And I get a quality of 88%, or 0.885, or if you like, 88.5%. By mass, the vapor is equal to 88% of the mixture. 88% of the mixture by mass is vapor, saturated vapor. So here we have by volume, almost all of it is vapor, but by mass, 88% of it is vapor. So I have a saturated vapor and I have a saturated liquid. The quality is 88.5%. Okay, 88.5%. Let's calculate the internal energy, U for the mixture. Let's calculate U for the mixture. So remember, this expression for quality can be extended to internal energy, specific internal energy. So I can have U mix, lowercase u mix, vapor and liquid in there. So if I want to calculate the specific internal energy for the mixture, I put U's in here and solve for U mix. So U mix is equal to U saturated liquid plus the quality times U saturated vapor minus U saturated liquid. I know the quality is 88.5%. All I need is the specific internal energies of the liquid and the vapor at 1 bar. Okay, at 1 bar. So let's get those things. Let's get those things. Okay. So just as a motivation, why are we calculating U for the mix? Specific internal energy for the mix. The total internal energy for the mix is equal to the mass of the mixture times the specific internal energy of the mix. That's why I'm looking for this. I know the mass, all right? So let's look up not V's, but U sat liquid and vapor. Okay? And we're going to get these from saturation tables, pressure tables, pressure tables. Okay, 1 bar. U, specific internal energy, U sat liquid, 417.36 kilojoule per kilogram, 2506.1 kilojoule per kilogram, saturated vapor, saturated liquid. So 417.36, that is for the saturated liquid, 417.36. 417.36 kilojoule per kilogram, and that's from saturation pressure tables. And then I've got 2506.1. 2506.1 kilojoule per kilogram for the saturated vapor. And that's again from saturation tables. Okay. Okay, let's take these numbers and plug them into our expression involving quality. Let's see here. U sat liquid, 417 kilojoule per kilogram plus 0.885, that's our quality, times the difference between the saturated vapor and the saturated liquid internal energy, specific internal energy. Notice say both terms have units of kilojoules per kilogram. And we crank through and we get a U of 2,265, 2,265.8, 2,265.8 kilojoule per kilogram, okay? And notice we are between 2,500 and 417. Better not get a specific volume greater than that of the saturated vapor, internal energy greater than the saturated vapor, or less than the saturated liquid, or you've done something wrong. Okay, so that's U for the mix, 2265.8. Let's plug in and calculate the internal energy. Let's see here, the mass. What was it? I guess I better check. What was the mass? Was it 0.01 or 0.015? 0.01 kilograms. And the specific internal energy was 2265.8. 2265.8 kilojoule per kilogram. The kilograms cancel out and I get kilojoules. And so I get 22.65 kilojoules. U mix equals 22.65 kilojoules. Box it up. That's it. All right? So that's our internal energy for the mixture. Quality is 88%. 22.65 kilojoules is the internal energy of our saturated vapor mixture. Okay? All right, we're going to finish off one last little thing, and then we'll be done. One last little thing. You might have noticed in the tables, there's lots of stuff in these saturation tables. Specific volume, specific internal energy, lots of stuff. If you look a couple of columns over, you'll see additional properties. So let's have a look here. Additional properties, internal energy, specific enthalpy. Don't worry about specific entropy. I know entropy scares the hell out of you. It should. It should. But let's deal with specific enthalpy. Enthalpy is a brand new property. So what is enthalpy? Enthalpy. E-N-T-H-A-L-P-Y. Enthalpy. Enthalpy is given by the symbol H and is defined as internal energy, U plus pressure times the volume of the system. So we have a system. It has an internal energy. It has a pressure. It has a volume. Therefore, it has an enthalpy H. H is equal to U plus PV. Okay? Now, I could divide this equation by mass. The H would become a lowercase h, U would become a lowercase u, and volume would become a lowercase v. So I can also define enthalpy in specific terms. Specific enthalpy is equal to specific internal energy plus pressure times specific volume. Okay? So I'm going to put a little box around this. It's up to you to commit to memory the definition of enthalpy. Specific or otherwise. Enthalpy. Specific or otherwise. The motivation here is you're going to see this quantity, H. You're going to see it in a lot of places. You're going to see U plus PV in a lot of places in this class. So they notice, thermodynamicists notice that internal energy is a property of the system. Pressure and volume are internal energy. Pressure and volume are properties of the system. And therefore, the product, pressure times volume, is a property of the system. So that means this whole thing is a property of the system. H is a property of the system. So why don't we just give it a name? We will call it enthalpy. We see U plus PV in a lot of places in thermodynamics. We're going to call it enthalpy. All right, ladies and gentlemen. Let me finish off by saying the equations that we used for quality also apply to enthalpy. So remember, we have this. X is equal to V mix minus V saturated liquid, V saturated vapor minus V liquid. Remember, we used this equation to calculate the quality in the previous problem. It also applies not only to internal energy and volume, specific volume, but it applies to specific enthalpy. So I can write this, H mix minus H of the saturated liquid, H saturated vapor minus H of the saturated liquid. So I can write this as well, and I can write it with U's. Remember, U mix, U saturated liquid, U vapor, U saturated liquid, okay? So I can write the quality equation and define it in terms of either vapors, I can define it in terms of volume, internal energy, or enthalpy, and therefore I can write this equation right here. So you should commit to memory the fact that you can rewrite this expression for quality and use quality for volume, specific internal energy, and specific enthalpy, okay? So that's just something you need to realize, all right? All right, ladies and gentlemen, that is done for this lecture.